myself and Professor Niladri Banerjee has from Loughborough University, we have a Spark project, and under that we are organizing this. So we would like to thank Spark initiative for allowing us to take this opportunity. Thank you so much. And now I'm going to ask Professor Tewari to start.
Okay. Thank you, Professor Chatterjee, for once again for for inviting me to present these tutorials. I guess I should start by sharing my screen again. Um, well, so do I have to?
Uh, you have been made presenter, I believe. Anupam?
So no, it says you are joined as an attendee.
Yes, yes,
That is
Oh,
that the
so can
reason?
you make him a presenter,
yes,
Anupam?
yes, ma'am, yes, ma'am. Yes, now
Okay.
Professor Tewari
Yeah.
will present.
Yeah, I can do it now.
Okay.
Let's see. Okay. So today I'm going to do sort of a blended presentation. So some of the stuff I'm going to walk out as I did last time on the whiteboard.
Sumanta,
Um,
can you increase your volume a bit? Because
oh,
I don't
sure.
know whether it is with me or with everyone, but I cannot hear very well.
Okay. Let me see. I think my volume is
100%. It's okay
yeah.
then.
Well,
Okay, maybe
can
there is some problem on this computer. It's okay. Please
okay.
continue.
Okay. But how about the others? Can the others
I,
hear me well?
Yes, we can hear. We can hear you clearly.
All right. Okay. So I was just saying that today's tutorial, I'm going to do some sort of a blended presentation because there is some stuff, mainly the Kitaev model, that I want to work out. No discussion of topological superconductivity, Majorana Fermions, and topological quantum computation and stuff. I mean, these things can be complete without a full discussion of the Kitaev model. That basically, even though Reed and Green, their 2001 paper that came out before Kitaev, and it perhaps it includes the essential physics of Kitaev model in the continuum language. Kitaev, though, gave a lattice description and also proposed monofermions for topological quantum computation. So essentially, most of the excitement about monofermions was started by Kitaev. So anyone who wants to understand these fields and wants to have sort of a complete understanding of what is going on, they need to be really familiar with that model. So that's one thing that I want to work out in full using a whiteboard. But the rest of the tutorial, today's tutorial will mostly talk about experiment. I mean, the system that is the most under experiment, which is the semiconductor superconductor heterostructure. I'm also going to touch upon the other systems that are talked about, not as much as semiconductor superconductor structure in terms of actual experiments, but I'm going to mention some of those, and those I'm going to do using a presentation because we need pictures and figures and stuff, experimental schematic and stuff. So those I'll do using my PowerPoint slides. Now, one thing I should mention: this is I'm going to use PowerPoint on my iPad. So maybe some of the lettering, some of the equations may not come out correctly. If they don't, then I'm going to try to write them down in real time. Um, I did most of it. but even if I miss something, then I have to correct it in real time. All right. So let's start with Kitai model. So Kitai model is basically is a model of one-dimensional P-wave superconductor. So we mentioned in the last tutorial that pinless Px plus IPy two-dimensional superconductor. We worked that out. That if you have a vortex in a 2D spinless Px plus IPy superconductor, the vortex will support a zero energy Majorana fermion mode. The same thing will happen in a 1D PUF superconductor, but we are talking about 1D now, so there is no Px plus IPy, it's just Px. And also because it's 1D, there is no vortex anymore. But there is still defects in 1D, which are the ends. The ends are defects because that's where the superconducting gap goes to zero. So there will be Majorana fermions at the end. How that comes about from a lattice perspective, that was shown by Kitai. I'm first going to give you sort of a qualitative description, and then I'm going to work out some, well, not all, but some of the essential math. So Kitai model. So there are two Kitai models in the literature. This is Kitai model of one-dimensional fermion. And so this is one-dimensional Kitai model. There is another Kitai model, which again many of you probably already know. That's a two-dimensional spin model that also has Majorana fermion. But that's a model for spin liquid and lots of other interesting stuff. Not much experiments have been done on the ideas derived from. Well, I mean there is some, but not much. The ideas derived from two-dimensional Kitai model. So we're going to talk about Kitai model in 1D or one-dimensional Kitai model. So suppose there are a bunch of fermionic sites, okay, in one dimension, and each fermionic site is described by a pair of annihilation and creation operators. Let's call them AJ and AJ dagger. So the first part of the talk, I'm going to I'm using Kitai's original paper. The second, I mean, first part of this discussion, Kitai model. The second part, when I'm going to actually do the math, I'm going to use a different reference. It's a book by Shen, Sun Ting Shen. So let's begin with Kitai's original paper. So suppose we have one-dimensional chain, and for each site on the chain, I have an annihilation and creation operators, AJ and AJ dagger. Now, associated with AJ and AJ dagger, as we discussed in the last tutorial, I can create two Majorana fermion operators, and let's call them gamma gamma 2j minus 1 equal to AJ plus AJ dagger, and gamma 2j equal to AJ minus AJ dagger divided by I. Okay. So because I have two Majorana fermion operators, I need to introduce these 2j minus 1 and 2j. So for instance, for j equal to 1, so for A1 and A1 dagger, I have gamma 2 minus 1, which is gamma 1 and gamma 2. For j equal to 2, I have A2 and A2 dagger. And for them, I defined gamma 2 times 2 minus 1, which is gamma 3. So gamma 3 and gamma 4, and so forth. J equal to 3, A3 and A3 dagger will have gamma 5 and gamma 6 and so on. So j equal to n, if I have n sites, then an dagger will have gamma 2n minus 1 and gamma 2n. All right, now consider the Hamiltonian for 1D P-wave superconductor. So the Hamiltonian is very simple. So you have H equal to sum over J and then minus P, that's the hopping, AJ dagger A J plus 1 plus A J plus 1 dagger AJ. That's the standard hopping sum. And you have a chemical potential term, let's say minus mu and AJ dagger AJ minus half. And then we have a superconducting pairing term. So delta AJ AJ plus 1 plus delta star AJ plus 1 dagger AJ. So that's the Hamiltonian written in terms of ordinary fermion operators. Now, as I said before, we define this gamma to j minus 1. That's a transformation, unitary transformation that you can do, aj plus aj dagger, and gamma to j equal to aj minus aj dagger divided by I. So we can invert this transformation. That will give you aj equal to gamma 2j minus 1 plus I gamma 2j divided by 2. You can just check that. It's straightforward. And aj dagger similarly will give you gamma 2j minus 1 minus I gamma 2j divided by 2. You can put these expressions over here in the Hamiltonian, and I'm not going to do the math. What you will end up with is H equal to I by 2 sum over j and then minus mu gamma 2j minus 1 gamma 2j plus P plus mod delta gamma 2j plus 1. Let's take delta real. Okay, so mod delta is same as delta plus but we don't really have to take delta real, but if you take a phase with delta, then it just makes the math look darker, a little bit more complicated. So let's just take delta real plus minus P plus mod delta and gamma 2j minus 1 gamma 2j plus 2. So that's what happens to Hamilton. So far, nothing has been done. It's just exact transformation. All right. And you can check this transformation at home. Those of you who are unfamiliar with the model, but maybe many of you are already familiar with it, but we'll go through it. So we're going to work with this Hamiltonian now in terms of the Majorana fermions. We're going to look at two extreme cases. So case A. So let's take mod delta equal to P equal to 0. Okay. And mu is not equal to 0. And in fact, we're going to take mu to be negative. Remember I said when we talked about the 2D skinless crystal IPO superconductor, I said that when mu is less than 0, negative, the system is non-topological. It doesn't have a zero energy Majorana fermion at the vortex place. And when mu is greater than 0, that was the phase that was topological. And that was the phase that had a zero energy Majorana fermion at the vortex place. So here I've taken mu to be less than 0. If I and mod delta and P are both 0, so these terms are both 0 now. So H in this extreme case is given by simply I by 2 and then minus mu and then sum over j gamma 2j minus 1 gamma 2j. And since mu is less than 0, this minus mu is positive. Now, so how does this Hamiltonian look like? I mean, if I so let's associated with that each lattice site of the original lattice, I now have a pair of Majorana fermions. So I'm going to draw a pair of Majorana fermions associated with each lattice site. So these dots are the Majorana fermions associated with each lattice site. Now, if you recall, gamma 2j minus 1 and gamma 2j were associated with AJ. So in this particular Hamiltonian, this particular Hamiltonian pairs the Majorana fermions on each side. So the pairing of the Majorana fermions are like this. So there is no Majorana fermion which is left unpaired. And minus mu is greater than 0. So this is basically this is it's Majorana fermions on each side are paired together on site, which forms a ground state with occupation number 0. Mu is positive. Now, minus mu is positive. So let's look at the other extreme case where I'm going to take mu equal to 0 and mod delta equal to c. And since it's mod delta, so it's greater than 0. So in this case, I have h equal to, now this term is 0. This term is also 0 because t equal to mod delta. So I'm just left with this term. So that term is going to give me a Hamiltonian, which is simply I t. So t plus mod delta will give me 2t. And we cancel this factor of 2 here. So it's I t sum over j and then gamma 2j and gamma 2j plus 1. That's what happens to the Hamiltonian. And now let's again draw the pair of Majorana fermions at each side. And now you see that it's the gamma 2j is paired with gamma 2j plus 1. Okay. So for instance, if I take let's say j equal to 1, then I have gamma 2, gamma 3. The next term would be j equal to 2 would be gamma 4, gamma 5. Okay. And if you look at this association here, so this gamma 2 comes from j equal to 1, gamma 3 comes from j equal to 2, gamma 4 comes from j equal to 2, gamma 5 comes from j equal to 3. Similarly, gamma 6 and gamma 7 will be paired, which means now the Hamiltonian pairs these two and these two and these two and so forth. So Majorana fermions from neighboring sites are paired. And if you continue in this fashion, then at the last site, this would be the pairing. And now notice something odd or something different has happened. Now I have one Majorana fermion here, which is unpaired, and one Majorana fermion there, which is left unpaired. Okay, so that's the difference between these two phases. And so now you have created, pictorially at least, you have created a phase of the system where you have an isolated Majorana fermion at this end and another isolated Majorana fermion on that end. Okay. Remember I said that each fermion you can think of as a pair of Majorana fermions. But now one Majorana fermion of one ordinary fermion of one Majorana fermion of one conventional ordinary fermion is paired with one Majorana fermion of a neighboring conventional fermion. And because of this pairing between neighbors, there is always one Majorana fermion is going to be left out on one end and another Majorana fermion will be left out on the other end. We can think of creating a fermionic operator using these two. Okay, but that, and you can associate a fermion operator with that with those two. So you can, I mean, I probably should have drawn that with a different color, but it's okay. So we can define well, I mean, we can define now ordinary fermion operator between neighboring sites. So we can call Cj. This is a fermion operator now. Not AJ. These are not AJ. Okay, AJs were the the conventional fermions that we created out of Majorana fermions on the same site. Okay, These are CJs. These are conventional fermions that you can create using Majorana fermions from neighboring sites. So CJ is, you can construct gamma 2J plus I gamma 2J plus 1. Okay? Remember, for J side, we had gamma 2J minus 1 and gamma 2J. And those gave me AJ and AJ dagger. But now I have CJ is gamma 2J plus I gamma 2J plus 1. 2J plus 1 divided by 2. And CJ dagger is equal to gamma 2J minus I gamma 2J plus 1. Divided by 2. If you do it, if you define your CJ and CJ dagger this way, then again you can invert and construct your gamma 2J and gamma 2J plus 1 in terms of CJ and CJ dagger, and then you can put them over here in this Hamiltonian. Again, you can do the math, it's very simple. You're going to be left with 2T sum over j equal to 1 to n minus 1 and Cj dagger Cj minus 1. Again, this is a phase in which there is no particle in the system, because again, the Cj dagger Cj is the number operator. If you put a particle in any of the Cj fermion states, you're going to increase the energy. So the ground state has no fermion. Ground state has energy minus, basically ground state energy minus T n minus 1. That comes from this term. Okay. But there is this state, this phase of the 1D pure superconductor has a twofold degeneracy. Okay. The twofold degeneracy comes from the occupation number of this conventional fermion. The conventional fermion that you can create out of these two end Majorana fermions. Okay, that state can be empty, which is going to have energy 0, or that state can be occupied by a fermion that will also have an energy 0. Why? Because that fermion operator does not even appear in the Hamiltonian, because those Majorana fermions are not there in the Hamiltonian. Okay, so if you put a fermion in these fermionic state, you're going to increase the energy. But if you put a fermion in the conventional fermion state that you can construct out of these end Majorana fermions, that is not going to cost you any energy, because those Majorana fermions are not even, if you look at this Hamiltonian, you see that it starts from gamma 2, gamma 3, and you're going to end. So gamma 1 is not even there in this Hamiltonian, and similarly gamma. So this goes up to n minus 1. So gamma 2n is not even there in this Hamiltonian. So you can put with impunity we can put a fermion in the conventional fermion state that you can create out of the two end Majorana fermions. That's not going to cost you any energy. So this state has a twofold degeneracy, which is topological. I hope this is, at least pictorially, this is clear to you that you have created a twofold degenerate state. By the way, this system is also isomorphic to, you can do a Jordan-Wigner transformation, and you can map this Hamiltonian of 1D P-wave, spinless P-wave superconductor into a transverse field Ising model if you do Jordan-Wigner transformation. And you know that the transverse field Ising model, it has a phase transition from the disordered phase, which has no degeneracy, to the ordered phase, which has a twofold degeneracy. It's just, the degeneracy is the direction of the magnetization. And that twofold degeneracy corresponds to the twofold degeneracy that I'm talking about here, is the conventional fermionic state that you can create out of the two end Majorana fermion state being empty or occupied. Now let me do this a little bit more mathematically now. I just sort of motivated, but let me just quickly do the little bit of math that's necessary to prove the twofold degeneracy and so forth. So I'm going to I'm going to do basically the same thing, but using slightly different notation now. So H equal to minus mu. So I'm going to write the same Hamiltonian. X equal to 1 to n, Cx dagger Cx. So instead of j, I'm just going to use x minus sum over x equal to 1 to n minus 1. So now, so that's the chemical potential term that I wrote before. So you have T Cx dagger Cx plus 1, okay, plus, now I'm going to include the phase of the superconducting autotomator, e to the power I phi, and Cx Cx plus 1, plus summation conjugate. So this is exactly the same Hamiltonian that I wrote down before, except now I have included the superconducting phase, phi, and also I've replaced the j with x, but x is still a discrete variable. So t is greater than 0, and mod delta by phi is the superconducting order parameter, and so forth. All right, so let's look at the special case that I talked about before. Mu equal to 0 and t equal to mod delta. This is the topological case. So mu is 0, so this term is 0. So I can write the Hamiltonian H equal to as, so, and I'm going to put this t equal to delta. So I can write this Hamiltonian as minus t sum over x equal to 1 to n minus 1. I claim that the Hamiltonian becomes e to the power I phi by 2 Cx plus e to the power minus I phi by 2 Cx dagger. If you just follow my math, I think it'll be clear. I'm going to work this out in real time. Will not take a lot of time. But I think it's important to actually work this out in real time. So it's e to the power minus I phi by 2 Cx plus 1 dagger. So that's what happens with the Hamiltonian. You might ask, well, how do I get this? Let's just check. So whether or not this is indeed equal to that. So if I expand, then I'm going to get minus t sum over x equal to 1 to n minus 1. Then this multiplied by that is going to give me e to the power I phi tx plus 1 minus, I'm going to get tx plus 1 dagger. That's from here and there. And then I'm going to get plus tx dagger tx plus 1. That's from this and that. And then finally, I'm going to get minus tx dagger tx plus 1 dagger, and then e to the power minus I phi. So that's minus t sum over x equal to 1 to n minus 1. And as you can see, I didn't need to do that. Cx plus 1. So I'm going to write this term first. So it's cx dagger cx plus 1. Um, that that's the t term, by the way. That's the t term. Cx dagger cx plus 1. These are fermions, so the anti-commute. So I can write this as plus cx plus 1 dagger cx. That's the Hermitian conjugate of this term. This term. And then I have plus e to the power I phi cx plus 1. That's this term. Mod delta is t, so I have taken the t outside. So I've left e to the power I phi cx plus 1. And then plus, again, I'm going to exchange them. So there is a change of sign. So cx plus 1 dagger, cx dagger e to the power minus. And you can see that this Hamiltonian is nothing but that Hamiltonian. So therefore, this is what I'm going to work with. Now I'm going to define. It's a little bit of math, but I'm going to take 5 to 7 minutes to finish this. So you can see that this operator is of the form Cx plus Cx dagger, and this operator is of the form Cx plus 1 minus Cx plus 1 dagger. So these are in fact of the Majorana form. Because you have Cx plus, these are constructed to be Majorana operators, even though they give you the Hamiltonian. So I can write H. So let me define those Majorana operators. So I can define gamma B with each site X. I'm going to define two Majorana operators now, gamma A and gamma B, gamma AX and gamma BX. I'm going to define gamma BX is 1 by root 2, exactly this one. So it's e to the power I phi by 2 EX plus e to the power minus I phi by 2 EX dagger, and gamma A, so this is gamma BX, this is gamma AX, is 1 by I square root 2, and then e to the power I phi by 2 EX minus e to the power minus I phi by 2 EX dagger. So one of them comes with plus, the other one comes with the minus. There's a factor of I in the denominator. That's the standard way we go back and forth between an ordinary fermion operator CX, CC dagger, and the corresponding Majorana operator. Now, if you look at the H, so then H is, you can write, so of course these give you gamma Bx, this is equal to gamma Bx dagger, this is equal to gamma Ax dagger. That's by construction, and you can check. So H therefore is, you have this as, so H I can write sum over x equal to 1 to n minus 1, and you can look at this. This is exactly gamma Bx, okay, with modulo this factor of square root. So I have square root 2 here, and this is exactly gamma A. So there's a minus sign, so this is gamma A, and this is gamma A x plus 1, and I get another factor of 2 and I, factor of 2 and then I, and then I also have minus 2. Sorry for the little bit of mess here. So this is minus 2it over x equal to 1 to n minus 1, gamma bx and gamma ax plus 1. This is what I said before. So now you see, since this is the topological phase that we are discussing, b equal to 0 and t equal to mod delta, you see that the Majorana fermion B from site X is paired with Majorana fermion A from the neighboring site X plus 1. Okay? So that's this pairing that I was talking about. So these two are paired, and so forth. So there's one at the end and one at the other end. So this would be paired with another one, and this one at the other end. So this one will be paired from one. So this one will be left out. These two will be left out in this case. So as I said, I can define a new conventional fermion operators that's using Majorana fermions from these neighboring sites. So I can write down dx equal to 1 by root 2 gamma a x plus 1 plus I gamma bx. So you can see that I'm taking one from x and one from x plus 1. And conventionally, and therefore 1 by, and dx dagger is then 1 by root 2 gamma a x plus 1 minus I gamma bx. Computing dx dagger from dx is trivial. All you have to do is just change the I to minus I, because the gamma operators are equal to their daggers. So so as you know, you can again take the inverse transformation and get write down the gamma b x and gamma a x plus 1 in terms of dx and dx dagger. Okay, what you're going to get is I gamma bx gamma ax plus 1 is in fact half minus bx dagger dx. So this is what I was saying before. H then is just minus 2t. So you have this I here, and then gamma bx, gamma ax plus 1. So that's exactly what I wrote there. You have minus 2t, and then sum over x equal to 1 to n minus 1, and then half minus dx dagger dx. So these remember, these are fermion operators, but they are fermion operators constructed out of Majorana fermions from neighboring sites. So you can write this as 2t sum over x equal to 1 to n minus 1 and then dx dagger dx. This is what I also said earlier, is minus n minus 1 times t. That comes from the factor of half. All right, so so therefore you have a bunch of d fermions associated with these operators. So this is, this is d1 dagger, this is d2 dagger associated with these pairings. Okay, those fermions cost you energy. The energy is t. So therefore the ground state is such that you have none of those fermionic states occupied. So the ground state has energy, so dx g equal to 0. That's the ground state. Ground state has no d fermion, okay, for all x. So therefore h, the ground state, is just this. That's the energy of the ground state energy. So minus n minus 1 t, the ground state. Okay, but now you note that in this Hamiltonian, what you are not going to find is um, let me write it here. In this Hamiltonian, gamma bn and gamma a1 are not there, because just put n minus 1 or x equal to n minus 1. You're going to get gamma b n minus 1 and gamma a n. Okay, but and also you start from gamma a2 when x equal to 1. So so gamma a1 and gamma bn are absent from this Hamiltonian. They are not even there. So which means, because those operators do not even appear in the Hamiltonian, you have gamma a1 comma h commutator equal to 0, and gamma bn commutator with h is also equal to 0. Okay, because those operators are not even present in the Hamiltonian. Which means that if you have a ground state G defined by these conditions, then gamma A1 G will also be a ground state. As most of you can see, that if there's an operator that commutes with the Hamiltonian, then you can write H gamma A1 G equal to gamma A1 H G, and this will give you this gamma A1 n minus 1 T, whatever the ground state energy with the minus sign, G, and you can bring this minus n minus 1 T outside gamma A1 G. So gamma A1 G has the same energy as the ground state. So therefore, you have three states now that appear to be degenerate: gamma G, gamma A1 G, and gamma B1 BN G. But it turns out these two states are not independent. I'm not going to show that. It's just to preview a little bit of math there. These two states are not independent, and in fact, so therefore, because these two states, you can actually construct another state from here. They are not independent states. I'm just going to skip a little bit of math there, and you can show that there are only two degenerate states, two orthogonal degenerate states, which are these G, and then the other one is 1 by root, which is the other one is a linear combination of these two states, is 1 by root 2 gamma A1 G minus I gamma Bn and of G. Now, if you look at my definition of these d fermions, this state is precisely the d fermion that you can construct out of those end Majorana fermions. So one of them comes with so there's a minus sign and there's an I. So this is precisely the d state that you can construct from so the state that you can construct by applying d dagger on G. So that's what I was saying before. G and d dagger G, these are the two states which are degenerate. And again, because the d fermion state has zero energy, because those Majorana fermions do not even appear in the Hamiltonian. Anyway, so that's topological degeneracy. These degeneracy you cannot really So first of all, these degeneracy we cannot perturb by any local perturbation because it's constructed out of operators that are far away from each other. And if if you are in this state, let's say there is a fermion in this D state, you cannot perturb this state into that one by any local perturbation. Okay, because again, we are talking about an occupation of a state that is very non-local. It's constructed out of wave functions that are on two ends of a chain. So local perturbations are not going to be able to displace the electron if it is there in this very non-local state. So this is why you cannot really make the state G to go over to state that, even though they are degenerate in energy. And therefore, these two states are ideal candidates for building a qubit, because any local noise is not going to be able to mix these two states. Anyway, so that's the essence of Kitai model. It shows that, at least in principle, it is possible to isolate single Majorana fermions in space, or isolate them spatially, and the result is a very non-local degeneracy, and this degeneracy can be exploited to build a topological qubit, which in principle you can now you go back to when I was discussing those non-abelian statistics, that you have a bunch of Majorana fermions now on your two-dimensional, but you can make other architecture, a bunch of Majorana fermions, and if you move one from the other, if you move one around the other, it changes the occupation number of these D fermions that you can construct out of pairs of Majorana fermions. So you can make unitary transformation in this degenerate subspace just by adiabatically moving the Majorana fermions around each other. Those will give rise to quantum gates. And these quantum gates are also immune to local perturbations because these are basically statistical interactions, like bosons and fermions. These are not actual interaction between these Majorana fermions. This is very mysterious, by the way. I mean, if you think about it, the Majorana fermions are in principle infinitely far away, and yet you move one around the other, always keeping infinitely far away. But something is happening, and the occupation number of these D fermions, these non-local fermions, they are flipping back and forth for all these D fermions that you can create. So if you have 2n Majorana fermions, then you can create n these D fermions. Each D fermion state can be empty or occupied. So you have created a 2 to the power n fold degeneracy, 2 to the power n fold degenerate ground state, and then you are moving one Majorana fermion and another. You are affecting the occupation number of these n D fermions. And those unitary transformations will be the quantum gates. So that's the essence of topological quantum computation. All right. So, but still, we talked about spinless fermions. So, how do you actually gate these things in nature? That's the question. So now I'm going to switch to some prepared slides. Let me see if it works. By the way, is there any question on this? On this stuff, Kitai Bob, or this was easy. Okay, all right. So let me move to. All right. So,
sir, Manipal Singh has a question.
sure.
You may please ask.
Yes, go ahead.
Good morning, sir. I have a question, sir.
Yes, go ahead.
Sir, the state G and D dagger G. As we have seen in the Kitaev chain, the two Majorana modes, one at the starting end and the second Majorana mode at the end of the chain.
Right.
They are especially very far away, but they are dependent on each other, not independent.
I mean, yeah, these states are not independent.
Yes, sir. Yes, sir. Gamma A1G and gamma BNG.
Yes.
So, is this feature is the topological non-trivial in the Kitaev chain model?
Oh, sorry, say it again.
Uh, is this feature makes the Kitaev chain a topological non-trivial?
Yes, this phase is the topologically non-trivial phase of the
Yeah.
Kitaev model.
And as you said that we can't perturb these states by local perturbation because they are spatially very far away from each other.
Exactly.
Yeah. So I'm asking a question. Can you go to the page where we considered the assumption delta is equal to t is greater than 0 and mu is equal to 0?
Right. Yeah. Actually, that's right. Thank you for reminding me. I forgot to make one final comment because everything that I discussed was just for one point on the parameter space. That's of course unphysical. It has to be phased over extended parameter region. But I'm going to comment on that. But go ahead. Let me
Yes,
just
sir.
answer your question and then I'll make a comment on that. Yes.
Yes, sir. My question is mu is 0 is very ideal condition, we can say.
Oh, I
Because,
see. Okay.
yeah, yes, sir.
That's true.
So my
Yeah.
question is that if mu is not equal to 0, it's still less than t, but it's of some order.
Yes.
So
Okay.
what will
Okay.
happen? The Majorana modes will exist or not, or if they exist, they will be robust or not?
That's a very good question, and that's precisely the point that I forgot to mention. And I thank you for asking me that because that reminded me, and I kind of guessed what you were asking, and it's a very perceptive question, by the way. So in reality, of course, I just talked about one point in the parameter space. But if something is valid just for one point in the parameter space, then that's useless because that's the fine-tuned point. But you can show by writing down. So you just write down the Hamiltonian and calculate the spectrum. Okay, the energy eigenvalue. This has been done. The write down the spectrum, the energy eigen, so write it down in the continuum limit and then calculate the spectrum. What you're going to see is if delta is not equal to 0, meaning you are in the phase with superconductor, you need superconductivity, then it is not just mu equal to 0 where the topological phase is there. It is in a range of mu, mod mu less than 2t, so 2 mod t. That's the range in which the topological phase is stable. So there is one point about topological phase that you need to be aware of. A topological phase, if you can show that it exists at one point in the parameter space, then if you move away from that point in the parameter space, as long as the gap does not close, the topological phase will still be there. This is related to the topological protection that I talked about in the previous lecture. Remember, if these Majorana fermions, specially localized, isolated Majorana fermions are created, you cannot really get rid of them just by a local perturbation. So if you move away from mu equal to 0 a little bit, that's a local, that's a small continuous perturbation. But remember, I said that if you have an isolated zero energy state and then a bunch of other states which come in this plus minus epsilon pairs because it's a superconductor. So if you have a state at plus epsilon, you'll have another state at minus epsilon. But if you have a state at 0, single state at 0, okay, you by making a continuous perturbation to the Hamiltonian, your continuous change to the Hamiltonian, you cannot get rid of this state because if let's say you could, so let's say you could get rid of this state and make, so let me call this plus minus e. So let's say you could destabilize this state and make its energy plus epsilon. But then because this is a superconductor, you must also have a state at minus epsilon, which means you are actually increasing the total number of eigenvalues of the Hamiltonian. And that is not allowed or a continuous change to the Hamiltonian. The eigenvalues can move and can change, but the number of eigenvalues are not that easy to change. In fact, there is a this is one of the concept, one of the corollary of version of some Lubel theory, that the number of eigenvalues is usually conserved. So therefore, if you have a single non-linear Majorana fermion localized spatially, and there isn't another one. Remember, the other one is on the other end, which is infinitely far away, very far away. So their wave functions do not overlap. So I mean, that's the assumption. The wave functions do not overlap. So they cannot really destabilize each other. So therefore, these Majorana fermion cannot go away. The only way it can go away is if you have a topological quantum phase transition. Okay? Because when you have a phase transition, then you have a bunch of other zero energy, because the gap collapses. So a bunch of other zero energy states that all come down to energy zero. So this conservation of zero energy states, that is no longer valid. So if you have to, if you have to destabilize a topological phase or non-linear Majorana fermion, your gap must collapse, and then on the other side, when your gap opens up, that phase could be non-topological. Okay, so so now coming back to your point, so if I could show the existence of a topological phase and the existence of a non-linear Majorana fermion on one end, and then if I could, by writing down the spectrum, the energy eigenvalues, if I can show that if you move away from mu equal to 0, the gap is not collapsed. Gap collapses. In fact, this is the point where the gap collapses. If mu equal to either 2t or mu equal to minus 2t. Those are the points where you're going to have a topological quantum phase transition. And on the other side of those parameters, these Majorana fermions will go out. Does that make sense?
Yes, sir. Yes, sir. So basically,
Okay.
the limit is mu is equal to 2t.
Mu equal to 2 mod t. Yes.
Yes, sir.
So there's a range in mu in which the topological phase is stable.
Okay,
And
so
only if
basically,
you
when we increase the mu and we get mu is greater than 2t, we are closing a gap and then reopening. So we are getting a topological trivial phase.
exactly.
Okay.
Exactly. And in fact, if you look at this Hamiltonian,
Yes.
and let's say you write it in the continuum limit, okay, this is a discrete Hamiltonian, I mean, on a lattice. But if you write this down in the continuum limit, okay, then you will see that the same quantum phase transition happens not at mu equal to 2 mod t, but in fact at mu equal to 0. So one side of mu is less than 0 will be the topologically trivial phase, and mu is greater than 0 will be the topologically non-trivial phase.
Yes, sir.
Okay.
Thank you, sir.
So yeah, all right. Okay. So as I was saying, so let me now move to my prepared slides and talk about some experimental systems, and so forth. All right. So how do we actually get such fancy objects, Majorana fermions, in nature? Well, the first system where these things were proposed were the nu equal to 5 half fractional quantum Hall systems. That was in 1991, Moore and Reed. And there have been a fair number of experiments on the nu equal to 5 half. Probably I should write it down here, nu equal to 5 half fractional quantum Hall. So nu equal to fractional quantum Hall system. It's also called Pfaffian, Pfaffian, Pfaffian fractional quantum Hall systems. There have been a fair number of experiments on this system, but unfortunately, no one has got any conclusive evidence of Majorana fermions in this system. But there has been a lot of experiments in this system. The second system that comes to mind is the chiral p-wave superconductor or superfluid. Remember, we said that spinless 2D spinless px plus IPS superconductor will have Majorana fermion, 2D or 1D. But of course, no, you don't have spinless PF superconductor. But what you have is, or could have, is chiral PF means basically px plus I2 superconductor. So that's called chiral PF. So strontium ruthenate is one candidate. Strontium ruthenate right here. Hello, hello,
Yes, sir.
hello. Yeah,
Yes,
did
sir.
I get cut off?
No, no, no. It's all right.
Oh, okay. Because okay, all right, good. And for a moment I thought my connection went off. Okay, so strontium ruthenate.
So the
For
presentation is now gone. Actually, we cannot see
oh,
the
the presentation is gone.
slides. Yeah, we cannot see the slides. Yeah, now it's okay.
Okay.
Now it's gone again. Actually, it's coming and going. Yeah.
Oh, really? Hold on. So what is so is my
Yes, now we can see
share?
your teams.
You can see what?
Your teams, Microsoft Teams.
Okay, but should I share my PowerPoint instead of sharing my screen? Maybe that will work.
I think, sir, you can try once more and then we can check. So if you
Okay.
yeah,
Hold
open the
on.
power.
So okay, is it? Can you see it now?
Yes, yes.
You can see it.
But we can see
All
it
right.
in a small window. It is not full screen.
Really?
We can.
How about now? Okay. Let me share my PowerPoint then.
Yes, sir. You
Let
better
me
share.
check by sharing PowerPoint. Share PowerPoint. Okay. Really? That's unfortunate. What should I do? Go to application. Can you see anything here now?
No, sir. Actually, now we cannot see anything.
So far it was working okay.
Yes.
Share my screen. So start broadcast again. Okay.
Now we can see your. Yes. Yes. Now it is fine.
You can see now?
Yes.
Okay. And the entire screen?
Yes, sir.
Okay, great. And I'm not. I'll try not to mess with the screen now.
Yes. It's up.
Okay. All right. As I was saying, for a long time, people thought that strontium ruthenate might be. Are you there? Hello.
Yes, sir. Yes, sir. We can see
Okay.
your screen properly.
Okay, but you can also hear me, right? Because sometimes the background noise that I am hearing, that is sometimes it's just stopping. But I shouldn't worry about that, right? I mean, you can hear me.
No. Yes, sir. We can hear you.
Okay, good. All right.
We
Okay,
can hear
so
you.
okay, great. If I do get cut off, okay, and I'm still talking and I'm not aware, then just please give me a call or send
Yes, sir.
you
I
can
will
call
let
me.
you know. Yes, sir.
Okay.
Yes, sir. Okay.
All right. Okay. Okay. So as I was saying, so strontium ruthenate, for a long time, people thought that strontium ruthenate was a chiral PUF superconductor. Now there is a little bit of debate about that, but at least, I mean, so this just at least one strong candidate is strontium ruthenate. But clearly, it is not a spinless PX plus IPF superconductor. Strontium ruthenate does have spin, which is why you need to have something called half quantum vortices in strontium ruthenate. Half quantum vortices are, just as the name implies, it's half quantum. So instead of hc by 2e, the flux that goes through a half quantum vortex is hc by 4e. Now, as a result of half quantum vortex, I mean, the magnetic flux being half, you can actually view a half quantum vortex as a full quantum vortex in only one of the spin sector. Okay, so if you have delta up up and delta down down, then a half quantum vortex in the entire system of strontium luthenate, you can write it as a full quantum vortex in only one of the spin sector. So then you are back to a vortex in a spinless PUF superconductor. So that's just one, one example where you can perhaps create a vortex in a spinless PF superconductor. But unfortunately, it is not, there is no consensus that strontium luthenate is in fact a PX plus IPY or chiral PF superconductor. Are you guys there, or have I got cut off?
No, sir, we can hear properly. It's
Okay,
okay.
all right.
It's all
Okay,
right.
okay.
Because there is no
All
background
right.
noise, probably you are having problem. Yeah.
Yeah. There is a constant background noise, and sometimes it's just stopping, and that's making me nervous.
No, it's okay. It's all right.
Okay, all right, okay. So the next one, so those are the two original systems that people thought, including us, that there could be Majorana fermions hidden in those systems. Um, the next system that was proposed to support Majorana fermions is this heterostructure made out of a topological insulator, 3D strong topological insulator, and SF superconductors. That was proposed by Fu and Ken. And finally, we proposed back in 2010 the semiconductor superconductor system. So what you have there is a semiconductor which is sitting in the middle in gray, and then on top of the semiconductor, so semiconductor has spin orbit coupling. As you know, many semiconductor do have spin orbit coupling. As you go to lower dimension, the spin orbit coupling in fact increases. So the spin orbit coupling is something that you need to create this topological superconducting state. Two other things you need a Zeeman coupling, and that Zeeman coupling in this picture is being provided by proximity effect of a magnetic insulator which is sitting below the gray semiconductor, and you need a superconducting pair potential which is being provided by this blue superconductor that's sitting on top, again by proximity effect on the semiconductor. So then the semiconductor has a topological state. I have not described or explained to you why, but it turns out that if you have these three ingredients, spin orbit coupling, a Zeeman field, and simple S-wave superconducting pair potential in the semiconductor, then these three ingredients conspire to give you a topological superconducting state that is analogous, that is similar to a 2D spinless PUF superconductor. So in other words, if you create a vortex now in this system, which is what is being shown here, there is a vortex created in the superconductor. Therefore, in turn, in the semiconductor also, because whatever superconducting properties are there in the superconductor are being proximity induced on the semiconductor. And that vortex is then supposed to support a Majorana fermion. I'm going to talk about that in more detail. There are other candidates, and some of which you were mentioning in the previous tutorial. One of them is copper dope bismuth selenide. So bismuth selenide is, of course, is a strong topological insulator. If you dope, then it becomes superconducting. It's a time reversal invariant. It is supposed to be a time reversal invariant topological superconductor, which is in class D3. That's actually different from the semiconductor superconductor heterostructure that is in class D. So the difference is, if you look at the semiconductor superconductor heterostructure, the time reversal symmetry is explicitly broken because there is a Zeeman field there. Copper dope bismuth selenide is time reversal invariant topological superconductor. Unfortunately, however, the signatures of Majorana fermion in copper doped bismuth selenide is still lacking. Meaning, this copper doped bismuth selenide should be analogous to helium 3b. Okay, now helium 3b has is supposed to have on the surface is supposed to have a Majorana fluid, meaning these are D fermion states on the surface. The bulk is, of course, gapped. That's the definition of a topological superconductor. As the definition of a topological insulator is that the bulk is gapped and the gapless states reside on the surface. Similarly, the definition of a topological superconductor is also the bulk is gapped and the gapless states reside on the surface. The difference between a topological insulator and a topological superconductor is that the nature of these gapless states. In the topological superconductor insulator, the gapless states are ordinary fermions. In the topological superconductor, the gapless states are Majorana fermions. So therefore, if copper doped bismuth selenide is truly a time reversal invariant topological superconductor, it should have gapless Majorana fermions on the surface. Which means if you do tunneling spectroscopy experiments on the surface, you should be able to see a zero bias peak because there are a bunch of zero energy states on the surface. Now, back around 2014-15, there was, I guess it was Yoichi Ando's paper that claimed to have seen a solid zero bias peak. So there's a gap, the conventional S-wave superconducting gap, as you do tunneling spectroscopy, and then at zero bias, you see a nice peak forming. So that was taken as a signature of gapless states on the surface in a superconductor, and hence it's a topological superconductor. Unfortunately, the subsequent experiments did not find those zero bias peak. So it is unclear the status of copper doped bismuth selenide. There is another class of systems which are being talked about now, which is iron-based superconductors. Now, iron-based superconductor, as most of you perhaps know, is analogous to the electron doped high TC superconductors. It has spin density wave and superconductivity. And a very interesting system. But more recently, people have found that there is a band inversion hidden in the iron-based superconductor as well. So it has topological band structure, and of course, it also has superconductivity. So iron-based superconductors are thought to realize basically the Foucault system, the topological insulator plus S-wave superconductor, but instead of the S-wave superconductivity being proximity induced, as it is in the Foucault proposal, these iron-based superconductors are supposed to have both topological insulating property and the superconducting property intrinsic to it. Now, there have been some recent experiments, again, tunneling, this is STM now. They did find some evidence of zero bias peaks in iron-based superconductors as well. Finally, there's another system that people talk about, mostly from Princeton. This is Ali Yazdani's group. They have ferromagnetic atomic chain created on the surface of superconductors like lead. And these ferromagnetic atomic chains should also behave like a topological superconductor. I'm not going to talk about these other systems in any detail, but if you have any questions, you can ask me. The system that I am going to talk about in the rest of my time is this semiconductor superconductor heterostructure. Okay. All right. So let's move on to the next slide. Not that. Oh, how much time do I have? So we started at 12, so it's 1 hour, 10 minutes. Okay. Now, before I move on to semiconductor superconductor heterostructure, I thought I should mention one other important concept that oftentimes you will see, and it's also being explored experimentally from time to time. So we talked about two sort of subtle concepts, topological protection and non-abelian statistics in the last tutorial. There is one other sort of subtle concept here, which is quote unquote teleportation. Okay, so what is it? So suppose you have two Majorana fermionic states, okay, at the two ends of a wire. Okay, or you have some two-dimensional system and you've created two vortices which are far away from each other, and each vortex has one Majorana fermion. And suppose all other states are separated by a gap in the system. So now, if you, let's say, you inject an electron in the system with the help of a quantum dot or something, then the only fermionic state available to the electron, in which the electron can go to, is this extended CC dagger state that you can create out of this pair of Majorana fermion states, gamma 1 plus I gamma 2 and gamma 1 minus I gamma 2. Which means if the electron does get into that state, let's say you inject the electron near Majorana fermion 1, okay, the electron is bound to appear near the Majorana fermion 2 after a certain time. Okay, so that's, it does not, I mean, it has to appear after a finite amount of time, even if the other electron is far away, other Majorana fermion is far away. So this has a sense of the electron being teleported, and it comes from this non-locality of this C state, CC dagger state. Now, of course, it does not break, causality or the speed of light. The electron does not have speed greater than speed of light and all that. I mean, we other people, including us, we have explored this phenomena, this teleportation phenomena. I'm not going to dwell too much onto this, but let me just mention that in this type of a system, there are actually three processes by which a current can pass through this type of a system, this type of a superconductor that supports a pair of Majorana fermion at the two ends. There is, of course, something called local unrave process, and many of you know that if you attach normal wire to a superconductor, the only way current can pass is the unrave process, because let's say an electron comes from the normal lead. The superconductor is, of course, gapped to single electron excitation. So the single electron cannot enter into the superconductor. So then how current goes through a superconductor? Well, uh, for some time, people really did not have an answer. I mean, experimentally, you see a current does flow through a superconductor, but the superconductor is gapped to single particle excitation. So how do the electrons enter into the superconductor? So that's where Andreev gave his explanation that the electron, when it comes to the interface between the normal metal and the superconductor that you see on the right, the little bit of the small picture I have there, the electron gets reflected as a whole. Okay, so then from charge conservation at the surface, a pair of electrons enters into the superconductor, and that's a Cooper pair. And the superconductor is gapped to single particle excitations, but it is not gapped to a Cooper pair. In fact, the number of Cooper pairs is not even conserved in the superconductor. So that's called an Andreev process, and this is the process in which charge is transferred in the superconductor, not by single charge, but a pair of charges, a pair of electrons. But anyway, so that's a local Andreev process. There is also something called crossed Andreev process, in which this reflection of a whole does not happen at the same point in space, but instead at a different point in space. So that's called crossed Andreev process or non-local Andreev process. That's also something that can happen in a superconductor. But now, if you have a pair of Majorana fermion at the two ends, there's a third process, which is the electron can be carried through these extended non-local state C and C dagger. So that's the Majorana assisted electron transfer. That's the one that gives rise to this teleportation like signature. All right, I'm not going to talk more on that, just to give you some sense of what people talk about in this field, the different currents, cross transitive reflection and so forth. Let's move on. So we talked about talked about 2D spinless PF superconductor and Kitai model. So we have already discussed those. So let's move on furthermore. So now let me just briefly touch upon the system of topological insulator superconductor heterostructure. Now, when I talked about 2D spinless P wave or 1D spinless P wave, the lattice version is the Kitaya model. I talked about the spinlessness. Okay. Now, the spinlessness is really, in reality, you don't have to have spinlessness. What you really need is a single Fermi surface. Okay. If you think about, condensed matter systems, um, Fermi surfaces almost always come in pairs. If you have not thought of it this way, but you have always seen it but accepted it without even thinking about it, because if there's a Fermi surface for the upspin system, upspin electrons, there is also a Fermi surface for the downspin electron. There's just no escape. It follows from Kramer's degeneracy. Even if you break even if you introduce spin orbit coupling, so there is no up spin and down spin, or even Zeeman field, small amount of Zeeman field, a generic chemical potential will give you a pair of Fermi surfaces. That comes from Kramer's degeneracy for any time reversal invariant systems. um, one Fermi surface corresponding to one spin, the other Fermi surface corresponding to a different spin. If you have spin orbit coupling, even then, those of you who are familiar with the band structure with spin orbit coupling, you know that there is always a pair of Fermi surfaces. Now, if you have a pair of Fermi surface, then it is not possible to create single isolated Majorana fermion. You can still create Majorana fermions. Those would be time reversal invariant topological superconductors, but those then you can have a pair of Majorana fermions at a point in space, but they will not be useful for non-abelian statistics or quantum computation, because they do not have if you have a pair of Majorana fermions at a single point in space, then their non-abelian statistics cancels each other. But anyway, so what you need is a single Fermi surface or an odd number of Fermi surface. That's really what you need. Not quite spinlessness. Spinlessness is one way to get into a single Fermi surface, or an odd number of Fermi surface. So the requirements are really odd number of Fermi surface or a single Fermi surface in the simplest case, plus superconductivity. That give particle symmetry is a consequence of superconductivity. That should give you isolated non-degenerate Majorana zero modes. Now, what happens in this topological insulator superconductor heterostructure is that those of you who are familiar with the 3D strong topological insulator, you know that on one surface you get an odd number of Dirac cones. Okay, in the simplest case, you have only one Dirac cone. Okay, which means this single Fermi surface requirement is already there. It's already fulfilled there. Okay, it's still time reversal invariant system. So Kramer's degeneracy is still valid, but still time reversal invariant topological insulator somehow evade this. Can evade this even number of Fermi surface situation by replacing the other Fermi surface to the opposite surface, of the entire system. On any given system, on any given surface of the 3D system, you have an odd number of Fermi surfaces. Those of you who are familiar with topological insulator, they know this. But anyway, suppose you have a single Dirac cone on a given surface, then that spinlessness, quote unquote, is already fulfilled. So all you need now is to have a superconducting pair potential, which you can by proximity effect. If you plaster a superconductor on the surface that contains the Dirac cone, then you have created a topological superconductor which can support this single non-degenerate Majorana fermion. So that's the essential physics of the Foucault system. I'm not going to talk more about that. There have been a fair number of experiments on this system without much success. So let's move on to the next semiconductor superconductor heterostructure. All right. So I said that getting this single or odd number of Fermi surface is very difficult because Kramer's degeneracy, which is valid for time reversal invariant system in the presence of time reversal symmetry, sort of forbids you to have an odd number or single Fermi surface. Now, topological insulator, as I said, evades that even number of Fermi surface property by moving the pair for the other Fermi surface to the opposite surface of the topological insulator. But the other way you can have an odd number of Fermi surface is somehow you have to break Kramer's degeneracy. And the way to break Kramer's degeneracy is actually break time reversal symmetry. So here I have shown you the band structure for a system that has spin orbit coupling. If you see the Hamiltonian, there's alpha. Alpha is the spin orbit coupling parameter. So there's a Rashba spin orbit coupling. And if you if you ignore this Vz sigma z, then the band structure is you have this and that. So those are the two spin split bands. Now, no matter what your chemical potential is, you're still going to get two Fermi surfaces. One is over here, the other one is the bigger Fermi surface. However, if you now apply a Zeeman field, then you create a gap over here, okay, at k equal to 0. And now somehow, if you can manage to restrict your chemical potential in the gap, then you have created a situation where you have a single Fermi surface. Okay. So now, if you can somehow bring or induce a superconducting pair potential on this single Fermi surface, you are done. So that's what you need. You need these three ingredients. You need the spin orbit coupling, you need the Zeeman field, and you need superconducting pair potential. Okay. This idea was first proposed in this paper. The paper that we wrote in the context of cold fermions, cold atoms. Okay. And also there's some of those similar ideas in that paper as well. Yeah. Okay. So the system based on the exact same ideas. Can you see? Am I still connected?
Yes, sir. Yes, sir.
Okay. So based on those ideas, we proposed the condensed matter realization again. So we have the semiconductor SM in gray that has the spin orbit coupling, the Rashba spin orbit coupling, and then I said that we need the Zeeman coupling to create that gap at k equal to 0. So that comes from the proximity effect of the magnetic insulator. The reason you need the proximity effect of a magnetic insulator instead of a simple magnetic field is because if you apply a magnetic field in a 2D system, magnetic field perpendicular is what you need. Parallel magnetic field to the 2D system is not going to work. But if you have to apply a perpendicular magnetic field to the 2D system, that will also create orbital effects, meaning vortices and so forth. So to avoid those complications, we just to have the Zeeman effect, just to have the coupling to the spins, we proposed to have this magnetic insulator and proximity effect of the magnetic insulator to the semiconductor. And the third thing you need is this superconductor to give you the superconducting pair potential in the semiconductor, again by proximity effect. The situation is simpler, a little bit, although the physics is identical, but experimental situation is a little bit simpler if you go to the 1D nanowire semiconductor. because now it's a 1D system, you can actually apply a magnetic field to give you the Zeeman coupling, because there is, you cannot really create a vortex in the 1D system anymore. So at least the magnetic insulator is you can now avoid. So you need this. So it's the same band structure that I drew before. So this is the gap, Zeeman field created gap, and you have to constrain your restrict your chemical potential in the gap. So that was the proposal. So Majorana condition is V Zeeman. So this is the Zeeman energy. V Zeeman is greater than square root delta square plus mu square. Okay. If you do not, so if the way to understand this Majorana condition is take the limit delta equal to 0. If you take the limit delta equal to 0, then this condition is basically Vz is greater than mod mu. Okay. And that's exactly what I said before. Remember, Vz is this gap. This gap is being created by the Zeeman field, and mu is mu is computed from this point over here. So the moment Vz is greater than mod mu, the chemical potential is in the gap. So this condition, in the absence or in the limit delta goes to 0, is exactly the condition that I talked about before, that you need a single Fermi surface. Where this comes from is a little bit more, the entire condition is a little bit more involved. For in order to do this, in order to get that condition, you need to actually solve the Bogoliubov-Djian equation for a vortex in this system. Meaning you have the Hamiltonian that has the kinetic energy plus, basically this Hamiltonian, that, this Hamiltonian in 2D. That was the problem that we solved in 2010. This Hamiltonian in 2D plus the delta terms, the delta, the superconducting term. So you have the kinetic energy, you have the spin orbit coupling, you have the Zeeman field, and then you also need to have this S wave superconductivity. So if you take that Hamiltonian and imagine that there is a vortex, then you have to actually solve the Bogoliubov-Djian equation corresponding to a vortex, the way I solved it for the 2D spinless P wave superconductor. Remember those Bessel functions and modified Bessel functions and so forth. So you have to solve similarly, and then you will get this condition, and this condition is the Majorana condition. So Vz less than mod mu, which means you are stuck with a pair of Fermi surfaces. Vz less than mod mu means this is the situation. Then this system is non-topological. Vz is greater than mod mu is chemical potential is over here. Vz is the gap. Remember, Vz is the gap. So that's the topological superconductor. All right. So what this means is that suppose you have somehow produced or observed superconductivity in the nanowire by proximity effect. This experiment has been done. In fact, this experiment was done even before we proposed this, that you have a nanowire or a semiconductor and you see superconductivity by proximity effect. Okay. So now this nanowire or the 2D system is a proximity induced S-wave superconductor that has spin orbit coupling. Now imagine you have applied a Zeeman field, a magnetic field. What happens if you have a superconductor and if you apply a magnetic field? Typically, the superconducting order parameter or the pair potential goes down as you increase the magnetic field. And for most superconductors, if you increase the magnetic field beyond a certain value, the superconductivity just goes away. This is called Chandrasekhar-Klogstone limit. Superconductivity just goes away. I mean, you can break a superconductor by applying a strong enough magnetic field. In this case, however, as you go on applying the magnetic field, the superconducting gap is going to superconducting gap. So if this is superconducting gap, let's say Eg, as you increase the magnetic field or the Zeeman field, the gap is going to fall. This is what is observed in conventional superconductors, and this phase is superconductor and this phase is normal. But if you have this spin orbit coupling in addition in the semiconductor, very surprisingly, the gap opens up again. Okay, and in this phase becomes a topological superconductor. This is Vz equal to this Vz equal to square root delta square plus mu square. This point, okay, and that's where the system has entered into this phase. That the chemical potential is in the gap created by the Zeeman field. Okay, and that's the topological superconductor. Now, this picture will allow you to understand it slightly a little bit more. In a conventional talk, I don't have enough time to go through these subtle points. So, but let me, since this is a tutorial, let me just go through it. This picture as well, even though perhaps you have now probably got the gist of the idea, but let me just elaborate a little bit further. So remember I said our goal is to get a single Fermi surface. Odd number of Fermi surface, but single Fermi surface is the simplest. Yes. You might say, well, why do you even need a spin orbit coupling on a semiconductor? Why can you not just apply a Zeeman field, and then you have a pair of Fermi surface, the top one and the bottom one, top one for the minority carrier and the bottom one for the majority carriers, and then you have your chemical potential in the bottom band, and then you are left with a single Fermi surface. That should work. There is no question that works in creating a single Fermi surface. However, this kind of Fermi surface will not allow you to have a proximity effect from a conventional superconductor, because notice here for K and minus K, this K and minus K, the spins are aligned in the same direction. Okay, so if you now place a superconductor on top of this system, you are not going to be able to proximity induce superconductivity if the superconductor is a conventional S-wave superconductor. You might ask, well, how about a P-wave superconductor? Well, who knows which system is a P-wave superconductor? And P-wave superconductors are notoriously problematic from disorder, this and that, and the solid P-wave superconductor is hard to obtain. So what our goal is to do whatever we can with S-wave superconductors. Now that's where the spin orbit coupling comes into the picture, because if you also have spin orbit coupling, then the spin orbit coupling creates a spin chirality. You can calculate the expectation value of the spin on the Fermi surface for this type of a band structure. And it's very simple. It's a single electron, single particle theory. And you can show that the spin actually rotates on the Fermi surface. Okay. So now if you look at K and minus K, there is, of course, a component of the spins which are parallel, but there is a tiny amount of spin component which are in fact anti-parallel. And that tiny component is directly proportional to the strength of the spin orbit coupling. So because of this spin orbit coupling, now it is indeed possible to proximity induce S-wave superconductivity. And the strength of this S-wave proximity induced superconducting order parameter will be proportional to the spin orbit coupling. So if you look at this Majorana condition, the spin orbit coupling does not appear anywhere here. It's the Zeeman field and the superconducting pair potential. But the spin orbit coupling is crucial, because without the spin orbit coupling, you cannot get the delta. Okay. So in order to get delta is in fact, if I draw that superconducting gap with Vz again, remember it falls as you increase Vz, then it opens up. But how, whether it opens up like this or like that or like this or like that, how strong the gap on the topological superconductors on the side, That depends on increasing spin orbit coupling. All right, so now that I have given you the essence of the physics here, let's talk about the experiments. So the first experiment following our proposal that came from Morik et al. In Cohen-Hoven's group. Are you guys still here?
Yes, sir. Yes, sir.
Okay. Is there any question so far? No question?
Hello, sir.
Yes.
Yes, sir. About this fact that after the applying the spin orbit coupling, I mean there is again gap opening up. So
Right.
how it is related to the P wave superconductor? I mean, can't it be D wave? I mean, I can't.
Well, that's a very good question. This is not quite the P wave superconductor. If you have, okay, so I have to. So suppose you have a. Okay, the short answer is this is not a P wave superconductor, because remember the superconducting pair potential is actually proximity induced from a bulk S wave superconductor. Okay, so the pair potential in the semiconductor is identical to the pair potential of this bulk S wave superconductor. So this is not a P wave superconductor, but this is an S wave superconductor that coexists with spin orbit coupling and a Zeeman field. Okay, so that's the short answer. But at the same time, you probably know that, or if you don't, then you should know now that if you have spin orbit coupling in an S wave superconductor, you can in fact write the order parameter as having components in the S wave channel and a P wave channel. That's just how to write, in the presence of, you have spin orbit coupling, so you can diagonalize your Hamiltonian, including the spin orbit coupling. It doesn't have to be the original bands. You can redefine your bands that includes the spin orbit coupling, Rashba spin orbit coupling, and then you can write your superconducting order parameter in terms of these new band parameters, these new band variables, and that will show that there is a component of the order parameter which is S wave, and there is another component of the order parameter which is P wave. So S wave and P wave are actually mixed if you have spin orbit coupling in the system. Okay, but that's just one way to look at it. But the short answer is the physics is derived from a bulk S wave superconductor, but you also have spin orbit coupling alongside the S wave superconductivity.
Thank you, sir.
All right. Okay. Following our proposal in around 2012, this famous experiment came out. And as you can see that they have, okay, this is the schematic of the experiment. So that's the nanowire. This superconductor is producing the, on top is producing the proximity effect. And then there are a bunch of gates. These gates are controlling the chemical potential. And there also has to be, there's a Zeeman field. So remember the condition, the Majorana condition is V Zeeman is greater than square root delta square plus mu square. Delta you do not have much control about, because delta is whatever delta is produced by the proximity effect. You can control V Zeeman but on the other hand, you cannot increase V Zeeman by B. You cannot increase B by very much, because increasing B also weakens the superconductivity in the system. So the other way to try to satisfy this condition is somehow to reduce mu. So these gates are for that purpose. You can try to reduce mu as much as possible by using these gates. Okay. Now they did all sorts of increasing V Zeeman, reducing mu, etc. And so these, and then okay, this is the lead that is being if there's a zero energy Majorana fermion here, then you will get a zero bias peak in tunneling conductance experiment. This is the theory. So the y-axis is differential conductance, dI/dV. The x-axis is the bias voltage, the voltage that is being applied here. Okay, you can see that the gaps are closing as you increase. So these are cuts at different B values or different V Zeeman. V Zeeman is proportional to B. So as you increase the V Zeeman this way, the gap is closing. As you know, that superconducting gap does close as you increase the magnetic field. But on the other side, you have a zero bias peak. This is experiment. So that's theory. Experimentally, you see what they found. So this is again dI/dV, the differential conductance or differential tunneling conductance against the bias voltage that is applied here. And as you can see, and again, these are cuts at different magnetic fields. So there is nothing initially at zero energy, but something opens up at zero energy. Okay, and it stays there at zero energy. So this part looks very similar to what is here. The part that does not exactly match is that the gap should close, but here the gap seems to be constant. These shoulders. So that was one problem that we noticed very quickly. But at least you find, as a function of magnetic field, there is a zero bias peak opening up, and the zero bias peak is very stable. Okay, stable means by applying, by further increasing the magnetic field, the zero bias peak seems to stay on until about this point where it splits. Typically, if you think about our conventional, D wave superconductor like the high TCs, if you do tunneling conductance near the edges, it is not unusual to see a zero bias peak. So zero bias peaks are not that uncommon. However, if you increase, if you tune different parameters, let's say if apply a magnetic field, those zero bias peaks quickly split, because in a high TC superconductor, you have upspin and downspin. So the zero bias peaks split essentially because of the spin splitting. So you get one peak that comes from one spin, the other peak comes from the other spin, and they split as you increase the magnetic field. But here, the zero bias peak is very stable, at least over a range in magnetic field. So that was pretty startling. On the other hand, the problem with with this experiment is that the gap is not closing. That's one. What you expect is the gap closes first, and then the zero bias peak appears at exactly the point of Zeeman field where the gap closes. That is not. That does not seem to be happening here. And the other problem is that if you have a Majorana fermion, those of you who know tunneling conductance experiments in superconductors, you know that if you have an unraved state at the interface between the metallic tip and your superconductor, typically the zero bias peak would be, or typically the peak heights, if it's an unraved state, not a Majorana state, but if it's an unraved state at zero energy, the peak height would be 4 E square by H. The prediction that if it's a Majorana state, the peak height would be 2 E square by H. So that's very important. 2 E square by H, 2 E square by H should be the peak height. So the height of these peaks should be 2 E square by H if it's a Majorana state over here. If it's any other zero energy state due to, let's say, impurity scattering, impurity state, or some other unraved state, the peak height should be or can be greater than 2 square by h all the way up to 4 square by h. Now, forget about 2 square by h, 4 square by h. The peak height that they found here is like 0.1 square by h. So it's orders of magnitude small, order of magnitude small. All right. Yeah, so that's what I said, fractional 0.1 times 2 square by h and sharp 0 bias peak, clearly separated from the bulk gap. Peak is only above a finite magnetic field, so that's good. Peak is only above a finite magnetic field. Peak robust against further increase of magnetic field, that's good, and consistent with topological superconductor interpretation. However, there are other scenarios which can also explain this zero bias peak appearing in this system. I'm not going to go over those. So there seems to be a smoking gun signature, which is that Majorana, if there is in fact a Majorana zero mode at the end of this wire, and if the metallic lead is indeed probing the Majorana zero mode, then this zero bias peak height should be quantized at 2 square by h, while the others are not. They can be above 2 square by h or below 2 square by h, typically, all the way up to 4 square by h. All right, so the status of the experiments until 1 or 2 years, 2 years ago, the zero bias conductance peak above a critical Zeeman field, that's consistent with theory if mu is close to 0. Remember, the condition was V Zeeman should be greater than square root delta square plus mu square. So they found that the V Zeeman that they find is typically of the order of delta. So that's consistent with, so this is V Zeeman critical. So that's consistent with theory if mu is approximately 0, which is not unusual because remember, we are trying to reduce mu by applying those gates. Right now, zero bias peak goes away for critical angles of the magnetic field. That is also consistent with theory. No convincing features for gap closure. This is what I was mentioning before. The gap does not seem to close as the magnetic field increases, but that also you can explain, and in fact we did explain that that's also not, I mean, you can explain that feature if your mu is close to 0. So that's not a big issue. So what could be the smoking gun? That these are indeed Majorana fermion. The smoking gun would be if you can indeed see the closing of the bulk gap, which would indicate the existence of a topological quantum phase transition. Because if you have a phase transition, that's when the gap closes. Meaning you are going from conventional superconductor, which is what the system is in the absence of the Zeeman field, and then you are increasing the Zeeman field, the gap is closing, and then it is reopening, then you know that you have entered into another superconductor. The bulk superconducting properties are the same. But now, if you also simultaneously see a zero bias peak, that's pretty strong proof that you have a topological superconductor with Majorana fermion. So if you see the gap closing, meaning the existence of a topological quantum phase transition, gap reopening, and a zero bias peak appearing exactly at the same point in the magnetic field, then that's pretty strong argument that you have created this topological superconductor with Majorana fermion. However, that's not what was observed. No experiment until today has been able to see this closing of the bulk gap and the zero bias peak appearing at the same value of the magnetic field. So you can do interference using Majorana non-locality. Those are much more difficult experiments. If you have Majorana fermions, you have to move them around, and you have these Arno-Bohm type experiments. If you could do them using the Majorana non-abelian statistics, but those are much more difficult experiments. Most experiments so far have been on tunneling conductance experiments. So that also has not been done. How about quantization of the zero bias peak height at 2 square by h? So that seems to be doable. Okay, that's still a tunneling conductance experiment. If you got your peak height to be 0.1 times 2 square by h, that must be due to some temperature effect or impurity or disorder effect or effect that has to do with the coupling of the metallic lead to the system. And maybe with refining more and more refinement of your experiment, maybe you will get there. You'll get a 2 square by h peak, the peak height. Now, is that a smoking gun experiment, smoking gun signature? We don't know. Until 2018, that's what people thought, that would be a smoking gun signature. Because if this peak is due to any other reason, like disorder or impurity-induced peak, impurity sometimes trap localized states. So if this peak is due to impurity-induced localized zero energy state, or due to some other reason, anti-localization and so forth that people thought about, typically there is no reason why those zero energy states will have a quantization of the peak height at 2 square by h. Typically in a superconductor, the zero bias peak heights are 4 square by h. That's a signature of the Cooper pairs. Okay, but remember, Majorana fermion is a single fermion. So it has peak height should be 2 square by h. All right. So until 2018, that's what people thought, that if you can find a 2 square by h peak, then you have done it. So this famous paper now retracted. In fact, this was retracted just a few days ago. This famous paper came out in Nature 2018, where they claimed quantized Majorana conductance. Okay. So you can see the claim here. We report a quantized conductance plateau at 2 square by h in the zero bias conductance measured in indium antimonide semiconductor nanowires covered with an aluminum superconducting shell. Our zero bias peak height remains constant despite changing parameters such as the magnetic field and tunnel coupling. That is, it is a quantized conductance plateau. So they are saying actually two things. Not only they have finally found a peak above a critical magnetic field, and the peak height is 2 square by h, but also the peak height is remaining unchanged as they change the parameters, magnetic field or the tunnel barrier height. In these experiments, you do need to apply a tunnel barrier height, tunnel barrier. So this is the schematic of the experiment. So this gray thing here, this gray region here, that's the semiconductor. The green is the superconductor. This is the metallic lead. This yellow is the metallic lead. You're applying a voltage here between the metallic lead and the semiconductor. And then there are a bunch of gates. These super gates are the ones that are controlling the chemical potential. And then there is a tunnel gate here. There are a pair of tunnel gates. Those tunnel gates are necessary to screen out the background tunneling. If you screen out the background tunneling by applying those tunnel gates, then only you will see a peak at zero bias. These types of peaks. So in order to see these types of peaks at zero bias, you need to screen out this background conduction from here and there. So you need these tunnel barriers. All right, so they did find finally this 2 square by h peak. As you can see, on these peak heights are exactly 2 square by h. So the black curves are for 0 Tesla. The red curve is for 0.88 or 0.86 Tesla. So that must be on the other side. That must be in the topological state, 0.88 Tesla. Yeah. So and this is theory. And as you can see, this DIDV peak height is 2 square by h. So this is the scale is 1. So it's about 0.8 Tesla. That's where it that's where it becomes 2 square by h, and then it seems to stay as 2 square by h. This is the actual spectrum experimentally measured, and you can see that this zero bias peak here is robust. Again, this is the DIDV as a function of the Zeeman field, and that's the plateau. So not only are they finding this 2 square by h peak, but also the 2 square by h height is constant as they change the various parameters. For instance, these are different other, this is where they are changing the tunnel barrier height, So, and you can see that the peak height is pretty constant. So it's a plateau. So not only do they have a signature of Majorana 2 square by h, but also the robustness of whatever is there at the end of the wire, that is further confirmation that it must be Majorana, because it's only the Majoranas which are that robust, topological robustness. All right. Many people declared victory, and was reviewed, in Science, Nature, Scientific American, you name it. Majoranas have been found. People, this is big deal, because if you can find Majorana, then you can do topological quantum computation. The main problem in quantum computation is really the noise. And all these superconductor-based quantum computers, superconducting qubits, it's still extremely difficult to get rid of the noise. But if you can get these topological quasi-particles, then Majoranas, then the noise is much less of a problem, for the reason that I described to you before. So this is really big deal, and people started thinking about how to build, architecture where you can move these Majoranas around, build gates, and this became big news. Okay, now in the remaining 10 minutes, or how many? There's just 3 minutes. I'll just take a few minutes to highlight our work on this. And in fact, this paper has now been retracted, not because of our work, but our work gave the first blow to the big claim in this paper. What we showed is that me and two of my students and another colleague of mine, Tudor Stanescu, we showed that it is possible to get these quantized conductance plateaus at 2 square by h with quasi-particles which are not Majorana Fermions. Okay, this is now well accepted. At the time we showed, let me it's just 3 minutes, but so let me just briefly say what this is now, part of the story that you need to know if you want to know the what is going on with Majorana Fermion. If you look at the schematics of the experiments, for instance, here you see that this is the region that is covered by, so this is the region of the semiconductor that is covered by superconductor. This is the metallic lead, okay, the yellow part. So there is always a region here, this given by this white region here, the green but marked as the white. This is the part of the semiconductor which is not covered by the superconductor nor by the metallic lead. So there's a quantum dot created there, and it turns out that quantum dot cannot be avoided. This band spectrum picture that they use to show that this quantum dot cannot be avoided in any of these structures. For instance, there is a quantum dot over here. It's from a different experiment. There's another experiment, and again there's a quantum dot over here. All right, now what happens in a quantum dot, those of you who are familiar with quantum dot in a superconductor surrounding, so if you have a superconductor on one side, a superconductor on the other side, and let's say you have a quantum dot which is clearly metal here, then the electrons can go and be reflected in the process called Andreev reflection, the one that I was describing before. And on this side, the hole can now get reflected as an electron in the reverse Andreev process. So you can create a bound state inside the quantum dot. Okay, it's an Andreev bound state. Now, what we did is that we modeled the quantum dot. So this is the quantum dot. How do you model the quantum dot? Well, quantum dot, remember, is the region of the semiconductor that is not covered by the superconductor. So the induced pairing, so this is induced superconducting pairing, that is going to 0 in the quantum dot. And the quantum dot, because it is not covered by the superconductor nor by the metallic lead, will have a different potential than the rest of the semiconductor. So it could be that the potential here is smaller than the effective potential in the part of the semiconductor which is covered by the superconductor, or it could be that the potential in the quantum dot region is higher than the potential in the semiconductor that is covered by the superconductor. This is the model that was taken by the Maryland group. This is the model that we took, and then we computed the spectrum. Now notice we have zero energy state here, but that's a pretty accidental zero energy mode because it is not robust. As you increase the Zeeman field, the zero energy mode is going away. Here, this is somewhat robust, but still not much. If you increase the magnetic field, the zero energy mode is going away. But notice here, you get a zero energy mode which is pretty robust to magnetic field. But this is entirely in the topological phase, in non-topological phase, because the gap closing is over here. So this is the topological phase. But in a long region in the non-topological phase, you have a zero energy, pretty robust zero energy state. That actually comes from this quantum dot. So we modeled the quantum dot like this, wrote down the Hamiltonian, diagonalized it, and this is the spectrum that we got. Now, why are we getting that spectrum? So this is the crucial slide that you want to understand, and then I can just flip through the other ones. So look at over here. This is a zero energy state, okay, as a function of Zeeman field. But this is an accidental zero energy state, meaning you need a lot of fine tuning to access this zero energy state. You know, if you just move your magnetic field a little bit to this side or that side, the zero energy state is gone. This would be the case. So this is 2. 2 is here. So this is a conventional Andreev bound state that sometimes crosses zero energy as a parameter is tuned. Okay. So here the Zeeman field is tuned. So this is a conventional Andreev bound state. Now, an Andreev bound state is something that I just described before using pictures. Andreev bound state is a conventional electronic state, fermionic state. So it's those C dagger. You can describe an Andreev bound state using those C dagger. But remember, I kept on saying that a C dagger you can also write as gamma 1 and gamma 2. You can define a pair of Majorana fermions in terms of C dagger states. Now you can draw their wave functions corresponding to those Majorana components of an Andreev bound state. Okay. For a conventional Andreev state, the Majorana wave functions will be on top of each other as they are here. As you can see, the two Majorana wave functions are on top of each other. They're actually red and yellow, but because in this region they are on top, that's why it's in a different color. It's a mixture of red and yellow. Okay, so the two Majoranas are tightly bound on top of each other, and this is why this Andreev bound state, you see this zero energy, but it is accidental. It's just zero energy is not robust because these are not Majoranas. These are two Majoranas on top of each other. This is mode 3, still a little bit robust, but not much. That's this. Again, the two Majoranas are on top of each other. These are actual, these are not schematic. These are actual results of calculations. What is happening here? Why is this robust? Although we are in the non-topological side. Well, the two Majorana components of the Andreev bound states have partially separated. Not exactly, but partially separated. But watch the consequence of that. So yellow Majorana and the red Majorana are kind of on top. They are strongly overlapping, but they are partially separated. But now suppose you are doing a tunneling experiment from this side of the nanowire. You are actually coupling only to the yellow Majorana, and the coupling to the red Majorana is exponentially small. Okay, this is the true topological Marana because it's on the right side of the gap closing. This 6 corresponds to this. Over here, the two components of the the two Marana components are fully separated. They are on the two sides of the wire. But and then you apply the metallic lead. You are going to probe this Marana, and that will be the 2 square by H signature, a robust plateau. But tell me, what is the difference between this situation and that situation? There is virtually no difference because you are, since your experiment is from one side of the wire, you are, even in this case, you are actually mostly probing just a single Marana because they are partially separated. Also here, you're mostly probing just a single Marana. So if all you are doing is probing the system from one side by a local tunneling conductance experiment, then this situation and this situation are going to look very, very similar. But this is a non-topological phase, partially separated quasi-Maranas, okay, completely useless for topological quantum computation because these objects do not have non-abelian statistics. This is on the other side of the topological quantum phase transition. These objects will be useful for quantum computation. These objects, these are Majorana wave functions. So that's what we did. So in Majorana zero mode is over here. So the two phases, two energies will come here as a function of Zeeman field. This is Zeeman field, and they will stay at zero energy. Andre bound state, as a function of Zeeman field, they can come to zero energy, and then but they will quickly go away from zero energy. That's in the ideal world. But if you have like a quantum dot or some other inhomogeneous potential in the system, it may happen that your Majorana wave functions that comprise a unwave state, they are partially separated, like over here. This red is one and the blue is one. They are partially separated. And using these partially separated Majorana partially separated unwave bound states, we could explain all the experimental plots, all the experimental findings. This is 2 square by H peak height, zero bias peak height as a function of Zeeman field, and you can see the plateau. So this is quantized. So this paper was quantized Majorana conductance plateau without non-abelian Majorana zero modes. Over here you can see the quantized conductance plateau at 2 square by H as a function of the dot potential. And this is as a function of the tunnel barrier height, barrier potential. You can see the plateau. This is for Majorana fermion. This is for partially separated unwave bound states. All right. So this is not the reason why the paper was retracted. The paper was retracted because of some problems with data. Okay. But the paper did acknowledge quite strongly that the alternative explanation is, of course, this partially separated unwave bound state or some other funny disorder, some other effect that. But we feel strongly that even if there is some other disorder effect or something, if you get a 2 square by H peak and a 2 square by H plateau, it must be due to this partial separation of the Majorana zero modes, which you can also construe them as quasi-Majoranas. And in fact, so these experiments came out from Netherlands, TU Delft, Coenhoven's group. And when the paper was being retracted, the main newspaper, Coenhoven is actually very famous in Netherlands because it was thought that he finally discovered Majorana fermions. But when it was retracted and all that, their main newspaper, the New York Times, or Times of India of Netherlands, they made it in the news. And in fact, they did my interview at that time, like 3-4 weeks back, and included my comments along with some other comments from other people. But anyway, so that's the story of the status of Majoranas. Now the question is there a way you can disentangle these quasi-Majorana or partially separated unwave bound states from the topological Majorana. This is an experiment where you can do that. It turns out you can with existing state-of-the-art experiments. You can of course do these interference experiments, I don't know, Bohm type experiments and so forth, but those are much harder. But in order to use, whatever we have, one can do two-terminal charge tunneling. I don't have time to discuss this, but let me just briefly mention the gist of the idea. The idea is, Majorana fermions are always created in pairs, right? Because my underlying objects are electrons. So if you have these C dagger electrons, if you create one Majorana fermion, then you must create the other Majorana. You have to create the other Majorana fermion. You can spatially separate them to make their, to give them their own identity, but still you have to create them in pairs. Which means if you have this 1D wire, and if you have one Majorana fermion here, you must have another Majorana fermion here. So suppose you do a three-terminal system. So you have a superconductor here, you have a metallic lead here, you have a metallic lead here, and you have a superconductor here. And then you are applying the Zeeman field, B. The critical value of Zeeman field where this one appears, at the same value of the Zeeman field, this one must appear as well. Therefore, if you do tunneling conductance experiment, and suppose you get the zero bias peak from this end at a critical value of BC, if you then do a tunneling conductance experiment from that end, you must get a zero bias peak at exactly the same value of magnetic field. Okay, and these are still finite system. This wire is not infinitely long. So therefore, these Majorana wave functions will still overlap a little bit. They are not exactly at zero energy. So when you do these tunneling conductance experiments, you are going to see oscillations, like this. These are oscillations of the tunneling conductance experiments. As you increase the magnetic field, this decay length of this, this is one Majorana wave function. There is another. This is one Majorana wave function. There's going to be another Majorana wave function. There's going to be some overlap. So, but this decay length of these Majorana wave functions, these are dependent on the magnetic field. So the overlap goes up and down, and which is why you see these oscillations. These oscillations, the oscillation that you're going to see from one end should also exactly correlate with the oscillation that you're going to see from the other end, if these are Majorana fermions. But if these are due to some other non-universal effect, like partially separated bound state, which is really the strongest candidate now to explain these experiments, then there is no reason to have this sort of correlation between the two ends. So that's the experiment that we proposed. That we said that this era of doing better and better local tunneling conductance measurements is over now. They gave the finest results that they could, but it doesn't give us a smoking gun proof of Majorana fermions. Existence of Majorana fermions. In fact, it looks like that it could be very well be partially separated bound states. So the way to go is to do these non-local experiments where you compare results from different ends and see if there is correlation. So those experiments have also been tried, are still being done. The situation is still in a flux. The big sort of declaration of victory that happened in 2018 has died down a bit. Our own research is now on quasi-fermions. I mean, we have now accepted that these are quasi-fermions, not Majorana fermions. So these are still Majorana components which are overlapping. The question is, can we do some sort of topological quantum computation? Perhaps not the purest form of TQC, but maybe some poor man's TQC where you have some topological operations that you can combine with some error correction processes. Are those? Is that possible to do? Some sort of poor man's topological quantum computation using these quasi-fermions. So that's the whole story of Majorana fermions and topological superconductivity and topological quantum computation in these systems. That sort of ends my tutorial. If you have questions, I'll answer those now. Are you guys there?
Yes, sir. Yes, sir. We are waiting for some questions.
Okay.
Hello, sir.
Yes.
So my question is, are these quasi-Majorana modes not capable for quantum computation?
Yeah. I mean,
Yeah.
they could be, but if you look at them, if you look at, let's say, their picture,
Still, they are giving the robust 2e square by h peaks, but they are not compatible for the quantum computation.
yeah, I mean, they will give you robust 2 square by h peak because you are because you are probing them from one side.
Okay,
So
so
therefore, your metallic lead is coupling to this yellow Majorana, and this red Majorana is far away. Is the coupling is exponentially small.
if you wanna, we can say probe the real Majorana fermions, we have to probe them non-locally from the both the ends, and if the results are same, then we can say that these are true Majoranas.
Yes.
Okay,
If the
sir.
results are perfectly correlated between the two ends,
Yes,
then
sir.
you know that these are Majorana. Because if the Majораnas are actually being created in the system, then they must be created in pairs. So if one end have them, the other end also should have the Majorana at the same magnetic field. And whatever effect that we will see as a function of the magnetic field from one end should again correlate with whatever you see as a function of the magnetic field from the other end. Those are the oscillations that I was talking about. Maybe the oscillation part is not completely understandable just by listening to one talk, but there is Majorana oscillations. But anyway, but yeah, I think you have got the gist of it, that the experiment that you get from results that you get from one end, if it exactly matches with what you get from the other end, then you know that these are Majoranas. Just to confirm even further, just 1 second, just to confirm even further, you can actually create an artificial asymmetry between the two ends. Let's say you can apply some local potential at the other end. This correlation between the two ends will still be there because Majorana fermions are not easily, you cannot really easily destroy Majorana fermions. So even if you artificially create asymmetry between the two ends, if whatever you are seeing are actual Majorana fermions, the two ends will still be correlated. But if these are not Majorana fermions but some non-universal, some other zero energy states, then of course if you create an asymmetry, there is no reason why the correlation between the two ends will survive. Yes.
Yes. Thank you, sir.
Yeah, Dr. Tewari, if I can ask a question.
Sure.
Yeah. I think there are two issues here. One is finding Majorana fermion. The other one is finding topological superconductivity. It is true that Majorana fermions can be seen in topological superconductivity. And the examples that you have given are essentially focusing on the finding of Majorana fermion.
Right.
Now, the issue is, I mean, when you do the proximity-driven superconductivity, all these heterostructures, it is generally found that it is S-wave. You don't find examples of P-wave insertion. I mean, you may find Majorana or you may claim it to Majorana there or not, but there is no evidence that in the heterostructures, P-wave superconductivity has been seen. So therefore, there is a fundamental question whether these are true representative of topological superconductivity. Whereas the copper, niobium, and strontium interconnected bismuth selenide, their P-wave Px plus IPy has been seen. And it's a very simple experiment. You somehow manage to do the surface probes, use surface probes, and you find nodal and nodeless characteristics in the, so for example, muon spin rotation measurements, where you measure magnetic moment associated with the Cooper pair. If you find magnetic moments associated with Cooper pair, then that's a p-wave superconductivity. So in particularly in strontium intercalated bismuth selenide, there is evidence to show that px plus IPY is realized. About the, so the point is, the quantum computation application point of view is more related to topological superconductivity. The way it is implemented now is the Josephson junction of niobium. But if you have topological superconductivity, maybe you can make greater application, more robust application of quantum computation. So focusing too much on the Majorana part may not be, we might be clouding the topological superconductivity aspect. That's my kind of just a comment, if you could. But strontium intercalated bismuth selenide, px plus IPY has been seen, and there the evidence is that the Cooper pairs carry magnetic moment. So there's clearly a p wave, and so basically you have a mixture of nodal and nodeless characteristics in the order parameter.
Okay, now that's a fair comment, but let me just respond to you by saying this. So what is the main signature that you expect to see in a topological insulator? How do you, what is the evidence of that will accept in favor of calling something topological insulator?
You mean
gapless surface?
Yeah, topological superconductor.
No, I'm talking about topological insulator now.
Gapless, yes.
That's gapless surface states.
Yes.
Right? So gapless surface states, those Dirac cones that people see in RPS experiment. Yeah, so those gapless surface states, right? The bulk is gapped. You see the gapless surface states, and if you have an odd number of Dirac cones, then you call it a topological insulator. This situation is exactly the same. Topological insulator has gapless fermionic surface states. Topological superconductors have gapless Majorana fermionic surface states. So if you do not see gapless surface states, it is very hard to claim it's a topological superconductor.
Okay.
And the example that you gave, if you do in fact have gapless Majorana surface states, which is the first and foremost condition for the system to be called a topological superconductor, then you should see a zero bias tunneling peak, because there are gapless states on the surface. If you do not see a zero bias tunneling peak on the surface, then it is hard to claim anything about topological superconductivity. Now, your other comments are obviously very fair. You may have seen, people may have seen PX plus IP, evidence of PX plus IPY. But so was the case with strontium ruthenium for a long time. But now, other evidence has emerged where people have taken PX, people have sort of taken back the claims about the same people that used to claim that strontium ruthenium is PX plus IPY. They now say that it's probably not PX plus IPY. So those are indirect evidence for topological superconductivity. The direct evidence for topological superconductivity of any system would be to see evidence of gapless surface states. Now, whether or not that's Majorana or not, that's even that's even a finer point. But at least one should see gaplessness on the surface.
Yes, that is true. But the STM measurement, the problem is to delineate actually the surface or edge state from the bulk state. Is not that trivial. So essentially, whether it is the zero energy gap, or whatever we're seeing, the peak, how do you really claim it is really the surface state or the edge state? So that the STM is the champion measurement, there could be some question marks from there also. RPS is the only measurement I know, but that's not a transport measurement. It's just a kind of reconstruction of the Fermi surface. So the other experiment is actually this muon spin rotation, where you actually measure magnetic moment only on the surface state, because then you can grind the samples to the typical length scale of the coherence length, and so you kind of measure on those grains only. And so basically the muons decay only at the surface. So the problem is, what do you call it the surface? I mean, what is the thickness or what is the edge over which you can say, even in an STM experiment, that these are confined to the surface state and no bulk contribution is coming.
Well, that's a good question. In fact, that's an interesting point. So you are saying that the muon spin rotation experiments, which I mean, I thought that muon spin rotation experiment is in fact a bulk probe, but you are saying that it is a surface probe.
Yeah,
And
you can grind it.
saying,
You can have the small grains of the crystals. You can grind the sample of this 2 micrometer, typically coherence or the penetration depth range, or the coherence length, and then thereby you increase the surface to volume ratio of each of your particles where the muons are getting embedded, and therefore dominantly you get the surface contribution only.
Okay, and what is the contribution that they have seen in muon spin rotation? The reason I'm asking is
they're in one of the strontium intercalated bismuth selenide, they have found px plus IPY.
But how? So what I'm asking is, I see your point, but so if it is a surface probe, I would be interested to know what would be the signature of Majorana fermions in muon spin rotation experiment. That's an interesting question. I do not know whether if anyone has answered. What would be the if it is a surface probe? What would be the signature of fluid of Majorana fermion on the surface? Because these systems are similar to helium-3b, so it's going to be a fluid of Majorana fermion on the surface. So what would be the signature of a surface of Majorana fluid in muon spin rotation experiment? I think that's a paper to write if someone can figure that out. If this experiment muon spin rotation is indeed probing just the surface. I think that's a very interesting point that you raise. I mean, instead of more than the order parameter symmetry, I mean, concluding or deducing the symmetry of the order parameter on the surface from muon spin rotation, personally, I would be more interested in finding out the signature of a Majorana fluid in muon spin rotation experiment.
Sure. Okay. Thank you.
And thank you for pointing that out. Maybe I'll look into that.
Thank you so much for doing this.
No.
Yeah, thank you so much. And I'm sure we will be in touch. And I'm sure from these 2 long sessions, one thing is clear, that when you join us, it is going to be very, very beneficial for this too. Thanks a lot.
Thank you.
Yeah,
okay.
all the best.
Okay, thank you.
Yeah.
Thank you. Thank you very much, sir.
Thank you. Thank you to all of you.